found that first it was written by Craig Summer in one of his reviews of TXRF. The dopant is assumed to not significantly change the optical constant of the substrate. So basically you calculate as if you had, suppose you have silicon substrate, you calculate optical constants for silicon, and then after calculating all the intensity of the electric field, you say, well, but there is
monochromatized by multilayer after passing silicon layers. The beam size which was incident on the target was 2 mm in diameter, and we had an average 2 times 10 to 11 photons per second incident on the target. Beam resolution was 6 eV for the two energies of interest, quantum metal, the aluminium K alpha line, and quantum metal.
And here you see every institute has got its specialization in one technique. This is my institute where we do SIMS and TOF SIMS. TOF SIMS is used for inorganic contamination. And then there is the Tom Institute where we do TXRF, and they also, which is used for inorganic contamination, so we'll be relevant on this stuff.
You have to think about the intensity distribution as A and B. A is where we see only a part of the intensity coming into the detector due to shadowing effects at the beginning of the detector, and B where the solid angle of detectors like a solid angle detection into
very reasonable values. So here are some ideas to prove the situation. For flux increase, the best pseudo source is synchrotron radiation, but you know it's sometimes really difficult to get the beam time there. So some laboratory ideas are high power, the photoelectric cross-section, special X-ray with special anodes or lighters, where you have here the silicon and it's alternating free space, silicon, free space. So this is how it is solved. These things are can be exposed to atmospheric pressure, but of course oxygen very well resolved in energies, and to do all alignment procedures motorized. You see the rotating wafer, this allows you to gain the polar coordinates, you reach a lot of points. Of course we have restrictions to the real final size. The jumper is, according to Austrian radiation protection law, an inherent protected spectrometer, which we like very much, and you have an ultra-thin window here, and the electron trap is in a separation of 6 millimeters. So the rest is described more or less, and you see the dimensions.
Well, this is the main layout of the TXRF beam line. Here is the schematic, so the drawing of the beam line. This is the service detector in the top of the sample. This is not very useful the polarization effect, but we use normally monochromatic beams, so we have reducing scattering in our sample. This is a silicon drift detector from Göteborg. Well, I'm going to show you some results of this. Well, here is the result for copper. We use copper at 100 degrees. We saw a very sharp peaks that we measured. So we made the theoretical calculations, and we have around the diffuse atoms in copper. About that, the principle of resolution is that if you change the term of the sample and normal angles, and in the text here we have at approximately 12 centimeters we have the slits, very small slits, that they collect the Grayson emission, the persons of Grayson emission. So we can wear the pattern by the different position, and we get the information of this for case of chromium. I will not go to talk about the roles here, we don't have to, but you can have I would follow and focus on chromium. Well, after that, there will be the consortium edge. Well, this is the standard solution for different arsenal oxidation Well, this is a
So what is behind this? Why is GI-XRF important? The detection of place element is important when it is basically surface basic science and applied science. Calculate the process in from each layer as well as the reflectivity. So basically, we start by putting the compare the layers, number of layers, thickness of each layer, density, taking the row, roughness, density, concentration of each element. And then you calculate the process. Project whether it is good or not. Again, you modify the parameters. Whenever you got good fit, then you can stop. Yes, this is a real research example of the system. You can see here wire structure, titanium, cobalt, titanium on deposited on silicon substrate. And similar things, I just reverse the things. Titanium, cobalt, and silicon. Cobalt, titanium, and silicon. So this is the process profile. Because since our program gives the process and reflectivity simultaneously, so you can measure both profiles. The reflectivity profile, calculated profile, and process profile. So basically, you can. So there are basically this method gives very reliable results because the process and reflectivity both are complementary to each other. Ultimately, one convert this good model come out from the age of the sample. And the people have used this structure like ESI and this electron. These are as a device. So this is the one-dimensional example, but this type of structure. And these are the results basically. So one sample, another sample where the marker is shifted to one sample. Two more. So you can see here this is the calculated results, fitted results, all is done by that thing. Basically, this I can explain this thing. Basically, this all this understanding in the case of one-dimensional potential well. Yes. So this is the process.
Thank you. Now we will measure the intensity at the contaminant time zone passes the radius down to the equator edge. So we measure, we prepare some bath with ammoniac, clean water and H2O2, and we put the contaminants inside, and by drying, by rinse and drying with the spin, we get this embedded type of lamination.
This direction of the rim divergence is also important. And I will explain some example of particle and another applications. We skip this one. Theory evenly by Göteborg, and we use the equation of Göteborg in the software. All the attendants can know this equation. Those are the example of the previous works, and there are those are the part of the list. And many works are done with a synchrotron radiation facility, and that we can see the same samples. This is the shape of that. We can see the very clear fringes. But actually, the divergence exists, and by changing the divergence of the incident beam, the shape deforms at this, and the fringes degrade. And our instrument have the detected experimental data, and the solid line is simulation. This is a very good fitting result, and this is a model to calculate the solid line. And the horizontal line shows the depth from the surface to the deeper position. And this means a nickel film exists this on the substrate. Substrate is soda lime glass. And the vertical line shows density of the elements. In this case, one system of nickel. And we deposit many different thickness of the nickel. Nickel is very easy to deposit to make a very uniform clear film. So I selected the element nickel. And then we did nickel intensity. And then this is the calcium intensity. Calcium comes from the substrate, the most intense element from the substrate. And we perform software assuming a rectangle shape or semi-sphere shape. And we give the two parameters for those structures. One is height and another is coverage. This is a calculation of the nickel. And if we give the height of the particle of 10 nanometer, the shape is like that. And in the case of the 30, the shape changes. And if we change the coverage, this means 5% of the coverage of the surface, and 10. The relative intensity of nickel and the silicon is changed. So by comparing those intensities, we can estimate the coverage. And unfortunately, we don't have the comparable calculation. No. And another is the gradation model. And when we make a slice in the sample and change the concentration by little we give the model of the gradation. This is the example of the arsenic implanted in the silicon. And in this case, the model is sliced, spacing is 1 meter. Function is given by the unsymmetry Gaussian in this case. And the last example is this. This is a synchronous of copper and gold on the soda lime glass. The spectrum at each angle changes. Depending on the angle, the intensity of gold is strong, and copper is strong here, and then calcium strong here. Profile is like that: gold, copper, and those are from the substrate. This is a scattered Mori intensity. And this is the data taken vacuum at 300 degrees C for 3 hours. Then take the angle dependence data again. The pattern changes from this one to this one. The big portion changes from the different portion to the same portion. And we can imagine this pattern shows two gold and then copper exist the same position. This means those make a uniform field. And we perform the simulation to those. This is an as deposit one on the glass substrate. We put the copper and then gold. And we perform the simulation, and the resulted value is of the thickness is 3.2 and 7.8. And the main fitting is performed considering the height and the position. And we cannot adjust this. There are some other deviations. And after the heating, we put a model on the uniform. The fitting result shows a gold of 47% and the kappa is 53%. Thickness is 11 nanometer. And when I calculate deposit
and the condition, correct condition. This is the real results. Again, I have used the same particle, 30 nanometer. Whatever I put on the silicon substrate, I put on that multi-layer substrate, same particle, same sound. So here in this silicon substrate, what I did is because the critical area is and also some oscillation on this thing. Yeah. So, but if you see that if this one and then add some oleic acid, then oleic acid works as an anti-agglomeration agent, so then allowed carrying multiple particles. And then ultrasonic dispersion of the particles like discussed. Then you can spin coating, one approach. Otherwise, you can use the dip coating, just dip the substrate. And then I have not put another step. Then you have to, because this is positive content, you have to remove it. Normally,
That's my report about the TXRF application of the waveguide resonator and about the properties of our small TXRF cell on base of waveguide resonator. The conventional X-ray line and intensity, radiation density in the area of the target will be increasing very much. Moreover, that approach, it is very interesting for study of buffer with the great diameters. Such approach allows to understand, to study of all surface of the buffer in the one procedure. But for this, we must using the polycapillary systems on the buffer and many detectors device.
And slopes of the calibration line, and what we concluded was that there is an influence of the sample shape is considerably. This was first simulation, so we cannot show now how it fits with the assumption of the real samples. So what we concluded is seems to be that the whole sample amount is distributed in many small, almost ideal TXRF samples, less self-absorption because of the lower extent.
Obviously, the course for near surface analysis. I would like to start with the first question: what is the surface? For example, here the surface of our planet, or clouds, they have also a surface for our skin. How to combine these three things with our idea of surface? It is nearly impossible to get a definition, so we proceed as mathematicians do, and we say that what the surface is our common knowledge about the surface, and we don't care about it because every definition will cause problems. For this idea, we go on and we think about a very simple surface, an even flat surface beneath what was the reflection of the trace. And it should be something like this here, some element, oxygen, or some electron clouds on the surface, something like this should be, but the most important thing should be flat and even. And what we are looking for is a real surface. Here we have some objects, particles, or some liquids with some ions inside. techniques which uses lasers for cutting, for welding, or for surgery produce nanoparticles. And these nanoparticles have some very strange behavior. The fine fractions of these remain in the atmosphere, and they were never when we are below the angle of the reflection. And here is the value for the background signal. So if we look at the differences, we have here in the case of the TXRF one-time signal as the background in the case of TXRF. If we put a droplet on a sample carrier and look via XRF, we have this spectrum. The same sample under TXRF, you see a lot of elements. What is the main difference? The background, the spectral background is suppressed. This here. What happens when you see a series of spectra? They were recorded during angle scan at the synchrotron facility. Some particles of carbon telluride were on the surface. Here we have the situation below the angle of total reflection. Then we can hear about the angle of total reflection and to see the signal of the particles disappear. There is only a little bit, and here really nothing. Additionally, we have here some copper and zinc. This is a contamination of the surface. We have a layer contamination, and the particles itself cannot be detected anymore. The intensity of the silicon is going higher because it was on a silicon wafer compared to the signal below the angle of total reflection. So at this moment, the world is completely in agreement with our knowledge. Total reflection X-ray fluorescence is a static mode for measuring. We have a condition which is fixed, and if we change the angle, we get the X-ray standing wave system. So, what is the difference? Only the change in angle, not only. For X-ray TXRF, we normally record a multi-element spectrum, but for X-ray standing waves, we choose only a channel or an element or more than one. It is possible to take 3 or 4 or more, and then we record the intensity of the channel compared to angle position. What happens? If we start with a very small angle, we have the condition here, some fringes only, and if we make the angle bigger, we got more and more interference fringes here. This is the X-ray standing wave system, which is well known since a long time, but unfortunately, this is not correct. We have to avoid this representation. Why? We have never taken into account that the coherence lengths of the X-rays are not big enough for fill the whole triangular section here of wave. I put here a certain value for a monochromator which is regularly used in synchrotron facilities. This is the spectral resolution, and according to this, we can calculate the coherence of this system. The longitudinal coherence is about 350 nanometers, and the transversal about 150 meters. So particles which are bigger than this are never covered by this field of installation for X-ray standing waves. So we cannot analyze particles or objects bigger than these sizes. And this is an optimistic view. Why? Here is the mode for calculating according to X-ray, the element of modern X-ray physics. And you see here, for the best result I could find in the internet, a very narrow molybdenum X-ray line from molybdenum K alpha, which was produced under special conditions with high percent above the reflector, which is covered by these fringes. The rest is only double intensity from incoming and outgoing wave without any interference. We are collecting the signals here for TXRF and TXRF and TXSV, and the reflected signals are used for the reflectometer, or the reflectivity of the surface. We go on. Not only here we have problems for the characterization of the system. We use normally this equation here, and we have to introduce a new function, the form function of the particle. This is one in the case of some crickets or some islands, and this is different for sphere, for example. When we look at the form of this, in the case of some nano islands, we have the of this type, or if we have only one size, one type of element here or here. Unfortunately, the smallest are not covered as well as the bigger ones. You see here the number of fringes crossing the particles more and more, and in average you have the double intensity. You have in the single places here 4 intensity, and the nodes and antinodes 4 or 0, and in average we have 4 times. But for small particles, only one or a part of the fringe will illuminate, so we have some deficiencies in the signals from the small particles. So we have a limitation in 2 ways. One way is the upper way, caused by the coherence length of the system, and the other one is the size of the particle. If we take into account the coherence, we have several problems. In the first case, the most difficult, we have one situation, same particle, different excitation. If you change the coherence and you excite the system, you will find first the well modulated, second you start in a higher position and you get this other way, then you get something like this. At least you have 10% of coherence illuminating your ball or your island. In this case, you will get really flat information, no modulation. In the case of 2 different particles on the same excitation, you get these results. However, you will never expect the coherence length on TXRF when we are using an internal standard. But different conditions for the internal standard. We have hydrophobic mixture particles which are impregnated, or crystalline hydrophobic particles, or amorphous particles, or some looking like cheese with holes, and you have some residue of your red, in this case red, internal standard, covering your sample. What happens? The coherence length is big enough, no problem. But if it's this case, we have problems.
Oh.
We are not illuminating, or we are not exciting our internal standard the same way in different positions. So this is an idea I had some weeks ago. This has to be proved if it's really or not. And then we have also problems with our internal standardization. That maybe that is the solution why we have this big scatter in TXRF. If I compare the repeatability of atomic absorptions with cosmology, you can, without any problems, 0.5% elevation. Nanoparticles, gold nanoparticles we produce in our institute with a very strong shot of femtosecond laser ablation of gold, and the XSV signal is shown here. At the beginning, we have some problems. We do not know exactly how we are illuminating the sample. Mostly we are making from the the side an illumination, and we have normal X-ray fluorescence. So we start with a value of 1, but what happens in the very low frequency, we don't know. These signals are corrected, so here's a signal of the reflection of the reflectivity of the system. Here's a signal of silicon, and here's outward signal. I put this value of controlling to this. In the same, we are looking for 2.5 square micrometers, and in the case of XSV, we are about 1 square millimeter we are illuminated. So we are not sure if we are in the right position, how much the influence of these big particles is present or not. The other experiment we have done, we calculated the composition of this. We make a simulation with 3 different particle sizes. You can fit the curve. Then I try to fit the curve because here in the beginning we have differences with this particle here. It's looking like this. These are single nanoparticles, but this is an operation, orthogonal operation. And the rest here, what we are not expecting, this is glass. The system, we store our sample. After ablation, we use very pure water. We stored it in a normal glass vessel with a plastic cap. And during 2 months, the water was dissolved in the glass. If you look for the elements distributed here, you will find calcium, boron, aluminum, silicon, potassium, elements present in the glass. So we have to take care where the particles are coming from before starting the analysis. So I have a brain. We need a standard reference material. Special design of regularly distributed metallic or non-metallic nanospheres of different sizes, but each size on one sample, please, and the surface of the paper or other materials. Obviously, a low-cost system. The answer? I had a dream. It is nearly impossible to position the sample in the way I would like to have it.
We have some process description, finally we have some standard operating procedures, some methods, some inputs, and so on and so forth. You see already a little bit, this is on the cover page of our that I have for several things. I have to give some, because the author drafted the final test to decide what they had of this small unit. We have to give version numbers and so on.
This is for direct example.
sample are exposed to the vapor phase of hydrofluoric acid, then all the surface layer is decomposed and residual impurities remain here. So it shows that only 5 or 6 times try to analyze the effect. She observed decomposed surface with sand and got this picture. Some 80 nanometers particle she found silicon membrane on the we measured solution sample and some biological samples. So this is a sample holder for solution sample. We have several and this is hydrated sample. And others are solution samples from 5 mol to 0.5 mol. So, and in case of sodium sample, we have powder sample, spectrum of powder sample, and powder. So, this is the sample holder, and this is the X-ray. So the question is,
if you the other accuracy much better, can be achieved much better resolution.
Okay, thank you again.
And together with teaching, which is a hard job, with most some of all have to do, and I also congratulate you very, very, very much for this, for being able to continue the group and to continue the level of X-ray spectrometry in Chalmers University. Not only X-ray fluorescence, but now TXRF fluorescence. So I'd like to ask you to join me to thank the organizing committee, especially Joan Bowman.
Yes.
Okay, now I keep the time because
I will tell something about some applications regarding food, medical, biological, and other applications. So, why do we care about selenium? Because more and more in the past, scientists have found out that there's a big fundamental importance of selenium to human health. And this is only a small part of it. But they have found out that it's an essential component for major metabolic pathways. I will not try to read it because I think I will get my tongue into trouble to try to say steroid hormone metabolism. And it's quite important for antioxidant defenses.
The composition of the matrix that could affect the performance of the determination?
Of course, we didn't use many numbers of matrices, but I think that the possibility to analyze in simple water gives a good idea that we cannot solve big problems of matrices, I mean from samples, from someone else, because simple water is more difficult.
And sodium magnesium solution were prepared by dissolving their respective salts. And different amounts of these solutions were mixed to prepare a multi-element solution, which was used for the calibration of the instrument. Detail I will be telling later. And this is the elemental concentration of various elements. You can see that sodium, magnesium, and aluminium. The resultant concentration is that calibration solution is 170, 45, 90.9 microgram per ml. And 1 ml of this is scandium solution, 1 ml of scandium internal solution was mixed with 500 micrometer of this solution.
For example, the contamination in the filter is higher than the total amount of trace elements which have been collected under the sample periods of 2 years. I have also collected compared to polycarbonate filters. Delta log dp means the difference between the logarithm of the maximum and the minimum diameter in the side spots. Ct is the total concentration of the trace elements, and delta C is the concentration in one size class. Here we see nickel, and we see that at both sampling sites, the peak in the submicron range is highest, and this is because nickel is a trace element of most anthropogenic origin. It arises, for instance, on combustion of coal or oil. This is the mass example I looked at. I found it a surprise. I mean, the samples have been collected in different sampling periods and at different sites. Still, they are nearly identical. We always assume
Instant X-ray intestines are closed. But yes. So our conclusion, compared with background reduction, freezing fluorescent X-ray intestines are more effective to improve detection rates.
And depth profile measurements. So basically, I will try to show you that using this technique we can do three-dimensional mapping of the elements in the samples. And at the very end, I will come to the point that this technique turns out to be sensitive for the morphology of the surface, and even with this technique we can measure and get some information about nanostructure of the surface. So the technique should be the same. So we started to work in this field just with some years ago, and the idea was just to think how to avoid the resonance Raman scattering. Metallic band crystal is used to analyze the X-ray, and the image is just detected by the CCD camera. So there is a beam, target, and the X-rays are refracted and detected by CCD. Basically, in this setup, one can use sleeve, but as I will show you later, which was important aspect of this technique. So, to give you some idea about the efficiency of course of the crystal spectrometer is very low, but on the other hand, we have very small Hamo spectrometer, so we are a little bit compensated this factor. The resolution is very good, 1 eV, and it was interesting that using it to check. We know that during the drying the droplet shrinks, and the diameter is 300. So you see the droplet just which was dried at a very high temperature. You see the remains of the original size. But this is a scan. We used micro X-ray fluorescence, the droplet residue with the resolution 700 by 300 nanometers. So it's really below micrometer. And this is the original size of the droplet, but we immediately realized that the temperature for drying should be small, about room temperature, and then you get the droplet size about 300 tiny details of this droplet, and you see here the picture. And here are just the scans over, let's say, this in this direction, and you see just these boundaries and this stuff here. After the drying in the low temperature, the shade is kind of round, but not very much smooth. But we use basically the existing energy of implantation, and you have very different profiles. So this figure demonstrates that this technique is good for investigations of the depth profile of elements. So next point, we have started very recently the new project when we realized that with this technique below the critical angle is sensitive for the morphology of nanostructure. So you really see very different features which are different for each one. So this result is as kind of perimeter.
As we know, that arsenic is not element, and we can have the situation of plants growing in soils enriched with the element, and some plants can accumulate big amounts of the elements, and these quantities can enter into TXRF.
We measured a lot of trace elements in body fluids with the TXRF. So to give you an overview, I will talk a little bit about sampling and how hard it is to get good samples without contamination. The sample preparation and how we get a homogeneous film on the sample carriers. I will give an overview about the element microgram per liter certified blank value, and for trace elements and body fluid, you can imagine even this is a lot. And then during the sampling, we try to refuse the first milliliters of the sampling needle, not to get the trace elements of the needle. For analysis, we use the parameters. Most of the time we use the molybdenum K-alpha excitation and
Son los terrones. Estos son los que me enseñan.
For the preparation of the sample carrier, we removed the silicone film in the inner spot where we prepare our sample, just to get a better position of our sample dot and a homogeneous sample dot. For whole blood and tissues, we use the digestion system, a microwave digestion, as you can see here with nitric acid and hydrogen peroxide. We always measure the reference material and the black blender with our samples. We get good results with the Oxford calculation for all these elements you could see here. The lattice we could measure in human levels because they are very high, but most of the mammals, the marine mammals we measured, they had lead levels beneath our detection limits. And here you could see the sample volume for these kind of samples. And we, of course, we could not measure these both elements and all elements beneath 10 microgram per liter. And because there's a big iron signal, we could get results for these elements, but they are not this big iron signal and want to do a real calculation for these trace elements. Doing a round robin test from distant NOAA for marine mammal blood, we measured with TXRF, get good results for these elements with the TXRF, and the concentration certified materials, they are comparable to seals from which we sample blood. There are other elements we have to measure with ICP because the concentrations are so low that we could not measure it right with the TXRF. So for plasma, serum, urine, and the other body fluids, we try to do another sample preparation just to get rid of a lot of contamination during the digestion system. after centrifugation and filtration, we diluted, like you can see here, we diluted the body fluid directly on the sample carrier with the internal standard and water. So you put it with our instruments. You can do that for nearly every sample. And what we could see here, the internal standard is the yttrium. It is well homogeneous mixtured with the other elements, and the peak of this is not real angle there. Also doing their measurements of reference material, we measured the urine reference material, and as you can see here, we got results for all these elements, but again, being careful with these elements. For example, for manganese, you get a signal and a calculation, but it's not the real one because of this influence of iron, the iron signal. Further investigated reference materials, you can see. So what we could measure besides the whole blood is, for example,
El serrano lo tengo en el laboratorio.
Where we get how do we get samples? We captured free-ranging seals in the North Sea with a net, investigated them, and then released them so we don't die and don't kill the animals. We get samples of seals.
Berlin and Paris and in the center, exactly in the center, both of this located. We had at the time 2 times the conference in Dortmund in 1988 and 1996, and the next will be the third. You are cordially invited. Thank you.
A few words before we leave. I thought it's just a few minutes since I stood here and welcomed you to this conference. But we think we want to thank all that has sponsored, supported this conference in some way. Everyone who have been working with lots of things. Working with me here in Göteborg, helping me with organizing this, and we have had great help from the International Committee with lots of input and preparation things. Since it's not the third time we have it here, it's the first time we have it, so much new things. But we have had an interesting program, I think. Lots of interesting presentations, lots of posters, and definitely lots of discussion. Immediately and continue like that. We have been very interested in your different works. That's good. And if you also are interested to spread this to a wider public, you are invited to submit articles to Spectrochemica Acta. And there are instructions in the book of abstracts. Deadline is end of September. But for this conference to be a good conference, we need some important people, and those ones we see here. Without those people, this conference would not be possible. So your contribution is most.
Something interior for your personal spirit. 24 karat gold.
So, you're most welcome out to some refreshments.
Thank you.